All right, guys, our next section in Chapter 12 deals with one of our first of two specific categories of sequences that we'll be working with in PCA, and that is an arithmetic sequence, okay? Our warm-up deals with an arithmetic sequence. It says, find the formula that defines the sequence 1, 4, 7, 10. All right, so that would be the first, the second, the third, and the fourth terms, okay? And if we just write out each one of the terms here, the first term is 1, second term 4, third term 7, fourth term 10. Okay. What we notice about the pattern from one term to the next is that we would be adding the same number from the previous term to get to the next term. Okay. This is indicative of an arithmetic sequence. When from one term to the next always comes from adding the exact same number, in this case the 3, that is an arithmetic sequence. Okay? Now, remember, we can find the formula for a sequence in multiple different ways. The first thing we'll talk about with an arithmetic sequence is how to define it recursively. Okay? So the recursive formula for this arithmetic sequence, I feel like it makes a lot of sense to think of this sequence recursively first, since we just talked about comparing one term with the previous term. Okay, so in this case, we would find each term by adding 3 to the term before it. Okay, and obviously if we were doing this specific term, we would have to say, let the first term equal 1. Okay, that would be the recursive formula for this specific sequence. Okay, we'll get to a little bit more generic way of writing that sequence here in a little bit when we get down to the bottom where we actually give a little definition. Okay, now what about the explicit formula for the nth term explicitly? Okay, remember, we will ask you to feel comfortable writing our sequences both recursively and explicitly. And to find the explicit formula, the first thing we're going to do here is kind of connect back to function notation, slope, things like that we learned, okay? So, if we think of this as a function, all right, think of it maybe even as a linear function. All right, when something from one term to the next is increasing by the same amount each time, we could think of that as a linear function, okay? So if this is our input and this is our output, so the first term, the 1, becomes our input, and when we input 1, we get an output of 1. If we input a 2, we get an output of 4, input 3, output 7. If we think of this as a function, and then we think of this, the increase from one term to the next, because it's constant, can we kind of think about this? That the slope of this function, if you will, this sequence as a function is 3, and it goes through the point 1 comma 1, or we're dealing with the point 1 comma 1. If we do that, okay, and we think of point slope form, so if we think of this as a function, and even a linear function, okay, because of the constant increase, if we put it into an equation, we get this. If we solve this for y, we would get this. Okay. Now, how does that relate to what we're doing here? Well, functions and arithmetic sequences can kind of go back and forth. So what if we replaced the x and the y with the nth term and the term number, just like we did here? All right, the 1, the term number, was our x, our input. The 1 as well was our output. Okay, we could do the same thing if we used the quote-unquote point 2 comma 4. If we used this here, it'd be y minus 4 equals 3 times x minus 2. We'd still get y equals 3x minus 2 after doing some algebra. Okay, and then we'd still come up with the same explicit formula. All right. And we came up with that thinking about an arithmetic sequence as a function, and that's one way to come up with the explicit formula for an arithmetic sequence. We will also lead us into the recursive formula will really lead us into a different option for our arithmetic sequence, the actual true definition of an arithmetic sequence, which we'll get right now. Okay, but again, nice to connect back, how sequences can act like functions. That was our first definition of what a sequence was on our first section of notes, that a function and a sequence can be thought of as input and output, and in this case, almost as a linear function. All right, math definition of an arithmetic sequence. An arithmetic sequence is a sequence in the form a, comma a plus d, comma a plus 2d, comma a plus 3d, dot, 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 where a is the first term and d is what we call the common difference. Okay. Now what you're going to see is that common difference, we've already talked about that, okay? This 3 here, in arithmetic sequence terminology, this is the common difference, or D as it's defined in arithmetic sequence terminology. The addition, whatever number is being added to each term, that constant difference between each term, that's what we call our common difference. Okay? We have a formula for the nth term of an arithmetic sequence. That is the true formula for the explicit formula of an arithmetic sequence. The nth term of an arithmetic sequence will be the first term plus the common difference times n minus 1. This n minus 1 will never change. This a sub n, or the nth term, won't change. The first term and the common difference will change. Okay? In our warm-up, we found that the nth term was 3n minus 2. Actually, I should go up here and change. I wrote a 1 here for some reason. That should be a 2. In our warm-up, we also could have done the following. The first term was 1, the common difference 3. We could have written our explicit formula like that. And that's how I would suggest. Okay. The nth term is the first term plus the common difference, always times n minus 1. Okay? If you were to distribute this 3 and combine like terms, you'd get 3n minus 2. Okay, so just to show you that they're both the same. And then also, so that's explicit formula. The recursive version would always be the nth term equals the term before it plus the common difference. Okay? Should make a lot of sense based on what an arithmetic sequence is, where we're adding the same number to each previous term. Next page. Gotta go to the back of that page. Forgot I printed two-sided. All right. So, example 1 asks us to find the first 5 terms and the nth term of an arithmetic sequence where a equals 2. That means the first term by definition, and d equals 3. So, the nth term will equal the first term plus the common difference times n minus 1. That will be our explicit formula. To find the first 5 terms, well, we already found the nth term. To find the first 5 terms, we could plug in 1, 2, 3, 4, and 5 for n, or in this case, if it's a common difference of 3, I don't really think we need to plug all those numbers into the formula. just knowing what the common difference is in the first term. This is easy math. Okay, if I ask you to do this, don't feel like you have to show me that you can plug in 2, 3, 4, and 5 here for this n and do a bunch of math. If you can just kind of add 3 to the first term, feel free to do that. All right. Example 2. Find the first 6 terms and the 300th term. Now, if I'm asking you for the 300th term, we're definitely going to need to find the nth term, unless you want to count 300 terms, okay, of the arithmetic sequence. Well, let's figure out the first term. It's 13. Let's figure out the common difference. Looks like it's -6. Okay. So the nth term equals the first term, 13, minus, in this case, or plus a negative, but we'll just write it as a minus, the common difference times n minus 1. Cool? All right, first 6 terms. I have the first and the second terms. Let's subtract 6 again. We get 1, subtract 6, -5. Subtract 6, -11. Subtract 6, -17. I don't need this fancy formula to do that part. I do, however, need this fancy formula to find the 300th term. Okay, so let's plug in 300 for n. And all we need to do here is a little bit of math. 300 minus 1 is 299. 6 times 299 is something awesome. What is it? -1794. So that's 13 minus 1794, which equals -1781. All right, good. Example 3, given the arithmetic sequence whose 11th term is 52 and the 19th term is 92, find the 1000th term. Now, this is interesting. All right. So the 11th term is 52, the 19th term is 92, and we need the 1000th term. So we definitely need the explicit formula for this, because we're not going to go counting up to the 1000th term. Okay, a couple different ways to think about this. All right, so we have the 11th term, and then we have the 12th, the 13th, the 14th, the 15th, the 16th, the 17th, and the 18th term. These are like blanks. I don't know what those are. I do know the 11th and the 19th term. Since this is an arithmetic sequence, we know we're going to be adding the same amount each time. Okay? How many additions will we have? Well, from 52, from the 11th to the 19th term, we are going to be adding 1, 2, 3, 4, 5, 6, 7. We're going to be adding 8 times. How did we know that? Well, 19 minus 11 is 8. So there will be 8 additions between the 11th and the 19th term. Okay? How many, what's the total of the additions for each of these terms? Well, it's the difference between the 19th term and the 11th term. So we're going 40 numbers in 8 additions. Okay? So you take the 19th term, we subtract the 52nd term. We need to move 40 units, basically, with 8 equal additions. We know it's an addition because we were told that it's an arithmetic sequence. If I divide this, that will give us 5, which happens to be our common difference. Okay? All right. 5 is our common difference. Okay? So we're going to have a 5 times an n minus 1. Okay? Now, how do we deal with the first term here? What is the first term? Should we count backwards 5? I guess we could. All right. There is 10 numbers to the left, so if we want the first term, and we have the 11th term, that's going 10 numbers backwards. 10 times 5 is 50. Take away 50 from 52. Our first term of this sequence would be 2. Okay. 5, common difference. I'm going back 10 places. 5 times 10, that means we'd be taking away 50. There's my formula. The 1000th term would be 2 plus 5 times 1000 minus 1. 2 plus 5 times 999. And you guys can just put that right into your calculator. think 4997.